The t-test is very well used, at least within the field of clinical medical research, and one might say even that it's overused. And it was invented in 1908 by William Seeley Gossett, who worked as a quality controller at the Guinness Brewery in Dublin. And when he published it, he had to use a pseudonym because the company did not allow him to publish his method, and he called himself student, and hence the student t-test. When performing a t-test in R, you use the t.test command, and you can use basically two different syntaxes. Either you write t-test and the first sample, the data from the first sample, comma, the data from the second sample, or you write t-test and then the column of dataset containing the observations, and then tilde the column containing the groups. And of course you can only have two groups in this column because the t-test accepts only two groups. And in this example we load the zip.csv file into memory and put it in the object D, and we then perform a t-test comparing the doses between individuals who have EM and PM in the zip29.3 column. So here I call for the doses and subscript this column using the genotype in the zip29.3 column, comma, the doses for the individuals with the PM genotype. And the alternative syntax would be to simply write t-test $dose, which is the doses, tilde the zip29.3, which is the group. Using the second syntax, we get this result. We get the information that we have performed the Welch 2-sample t-test, and that we have looked at the dose grouped by the zip29.3 variable. We also get the t-value, degrees of freedom, and the p-value, and as you can see it's highly significant here, the difference. We have a p-value of 0.0003. We get the alternative hypothesis, and the zero hypothesis is obviously that the dose is equal in both groups in the population. We get a 95% confidence interval ranging from 20.5 to 43.5, and this refers to the difference between the two groups, the difference in dose. And we also get sample estimates, the mean dose in each group, 41 or almost 42 milligrams per week in this group and 10 milligrams per week in this group, indicating that there is really quite a large difference. Additional arguments that can be added to the t-test are alternative. It's two-sided by default, but you can get a one-sided test using greater or less, and you would have to check out which one you should use in the specific situation. But my experience, at least from clinical medical research, is that it's very hard to convince a reviewer that you should use a single-sided test, and all the time you end up using the two-sided test. Paired is false as default, and R as default gives you an unpaired test. If you want a paired test, t-test, then you would have to set paired to true. And as default, you get unequal variances. That is, R accepts the possibility of unequal variances in the two groups. If you would like to force the command into assuming equal variances in both groups, then you would have to set variances equal to true. And the confidence level is 0.95 as default. And therefore, the confidence interval that you get is a 95% confidence interval. So, let's look at what the output of the t-test is actually, really. because obviously you get a lot of information in the console when you perform a t-test, and that's good enough if you just want to perform a t-test and look for significance and so forth. But a lot of the time you would want to, for example, extract the p-value and put it in a graph or plot or something, and then you would have to understand what the output of the t-test is. So in this case we put the output of t-test in a new object called tt, and we then ask R to show us the contents of tt, and we get the same text as we did previously. So one might be tempted to think that the t-test output is some sort of text, but it's not. If we look at the mode of the output, then it's a list. The class is actually age-test, which is a hypothesis test and a class of its own. And if we ask for a summary of TT, we get a presentation of the contents of the list, not actually the values, the contents, but we get to see what's in it. For example, statistic, parameter, p-value, and the confidence interval, which may be of interest. So this gives us an opportunity to extract information from the list. And if we want, for example, the p-value, we might write tt and use subscripting to get the third element from tt, which happens to be the p-value, and we get then the p-value. It may be difficult to remember the exact number of the p-value in this list, that it was element number 3, so instead you could write tt $p-value, which is easier to remember, and you get the same result, obviously. To get the confidence interval, you would write tt$conf_int, and then you get the confidence interval provided as two objects, actually. The first one is the confidence interval itself as a vector containing two elements, the lower and the upper limit of the confidence interval. And then you also get an attribute telling you that it's specifically a 95% confidence interval. And if you want to get only, for example, the lower limit of the confidence interval, then you would have to use subscripting within the subscripting, double subscripting, so to say, and write tt$conf_int and then ask for the first element in the element conf_int, and you would get 20.47 here. Now, the zip.csv file does actually contain matched pair of patients, and in the test we performed previously we used an unpaired test, which is the default, but it would be more correct to perform a paired t-test in this situation, and that can easily be done simply by adding the paired equals true argument to the t-test. And as you can see here, you get different values. Here you actually get a somewhat higher p-value than before, and that's not usually the case. Often you get a lower p-value and more significant results when using a paired test, but not in this case. And you get the confidence interval, which is the confidence interval for the difference between pairs, and you only get 1 point estimate here, because you're no longer interested in the mean value in each group, but you're more interested, and you should be more interested in the mean difference between the groups, because that's what you're looking at in the paired t-test. Now, when you're using a paired test, you obviously would have to get the correct matching so that the pairs are kept together. You don't match a person from one pair with a person from another pair, but that you keep the pairs together. And in the data set we used here, it turned out to be correct simply because the pairs were presented in the same order. First you had EM1, then 2, 3, 4, 5, 6, and 7, and then you had all the PMs in the same order. But if they had been in a different order, the pairing would have been incorrect. So a safer way of arranging your data set when performing a paired test may be to have one pair per row instead of one observation per row, and then put the two observations in the pair in separate columns. In this example, we put the EM from pair 1 here and the PM from pair 1 here, the EM from pair 2 here and the PM from pair 2 here. And by using this structure, it should be correct all the time, even if you reorder the rows of the dataset. And you would have to use the t.test command, providing the data as the first column, comma, the second column.